Hi class, this week's lab is volumetric analysis. This is building upon lab 9 that you did, which is titration. So we are doing a titration again, but it's going to be building upon it. So there's 3 steps to this titration that you're using. Volumetric analysis is a chemical analysis that is performed primarily with the aid of volumetric glassware. Procedure: a known or quantity or carefully measured amount of one substance reacts with a to be determined amount of another substance, with the reaction occurring in aqueous solution. What this means that with the titration, we are using specific volumetric glassware that removes a lot of inaccuracies with normal glassware that we would use, graduated cylinder and so forth. We use pipettes, we use a barrette. We try to keep this as accurate and precise as possible to remove a lot of errors that would be done otherwise, because we are trying to determine, in most cases, a concentration of an unknown. We have the volume, but we don't know what the concentration is, so we want to get that as accurate as we can. I'm not going to go too much into titration because if you have any questions about this or you're unsure, you can, 1, read this in your book. 2, titration, I did a video of this already. You can refer back to that one to help you understand. But it's really not any different. And I think even if you don't remember right now, as I go through this, it might be making more sense. Titration is a way of determining an unknown acid or base concentration in a solution using a known concentration and volume from another one. Fancy definition that LabFlow gave: a known concentration of a compound is added to a known volume of another compound of unknown concentration. The titration will be used to determine the concentration of the second compound. So what does this mean? You have a barrette and you have a known, in most cases it's a base. In this case, and I'm going to say in our case, it is the base. Sodium hydroxide will be in here. And we know the volume, and we will soon know the exact concentration of it, as accurate as possible. Once we know the molarity of this, we will then try to determine our unknown acid molarity, but we will know the volume here. And there are 3 sections to this lab. First, we're going to determine the molarity, which is going to go in here, of our base. Then we're going to determine the molarity of the unknown acid here. Then we're going to do a 3rd step. We're going to go even further and get a percentage. Percentage by mass, this simply means grams, of an acid in an unknown solid. So there's 3 parts to this titration, 3 different titrations that would occur if you were in person. Sometimes it's easier just to refer to certain names on a titration, so you don't have to be specifically, we don't know the acid, and you won't know through this whole thing which acid you have. You will be given enough information to solve, but you won't know the acid. It's never going to be told to you. So sometimes it's easier just to refer to certain general terms. In this case, whatever is in the barrette is a titrant, and whatever is in the flask down below that is dispensed into is the analyte. So in this case, the acid would be the analyte, and the indicator will also go in here too. And sodium hydroxide is the titrant. The indicator will always go in the flask. This is where the chemical reaction is occurring. And when it's based on a pH indicator, so it's clear in acidic conditions, so below 7. And so I don't necessarily agree with this part, but actually that's okay. Phenolphthalein is actually turns color above 7. It doesn't state that here. And turns pink in basic conditions. So when this changes color, the titration stops. So the analyte is here, the titrant is here. Here are some terms I put together for you. Titrations used to determine the concentration of an acid or a base in a solution by using another solution of known concentration of volume. Titrant, the solution with known concentration delivered into the unknown. In this case, it's in the barrette, and it's sodium hydroxide. Analyte, the substance of an unknown concentration, but you will know the volume. It's in the flask and is on the barrette. It's where it's being dispensed into. An indicator, in this case it's a pH indicator, is a substance placed in the analyte. It will change color when the solution reaches a certain pH. That is the endpoint, when the titration stops. Equivalence point. LabFlow refers to both of these, equivalence point and stoichiometric point. They are the same thing, but they use it, I think, to test you guys. So make sure you understand. It's the same thing. Enough titrant is added to react in exact quantity with an analyte to neutralize both. you cannot observe this chemical reaction happening. What is happening is we use a base and we use an acid, and they are neutralized if a certain amounts of both interact. A base and an acid are neutralized to produce water and a salt. So this is simply stating that the number of moles of an acid is equal to the number of moles of a base. This is just generic here, this HA and the BOH. So this would be your unknown acid. This is sodium hydroxide. That's what the B stands for, is base. When they are equal, then that's where you're at the equivalence point or stoichiometric point. They have been neutralized out. Endpoint, the point at which the indicator changes color. Ideally, it's the same as the equivalence point. What does that mean? Sometimes the equivalence point and the endpoint do not match. They're completely off. So you have to make sure you pick an indicator, call it a pH indicator, that matches your equivalence point or where it's supposed to be. If you do that, then these will match and you can stop the titration exactly at the same point. Neutralization. So you have an acid and a strong base. It will result in a neutralization reaction, which produces water and a salt. An acid solution loses a proton, depending on the strength, will determine how much it'll ionize. For instance, here I put up an equation of HCl, a strong acid with a strong base, produces water and a salt. So this being a strong acid completely ionizes, meaning it breaks apart completely and it does not get back together, where a weak acid, opposite, doesn't want to break apart at all. It gives very few protons up. So this being strong, it breaks up completely. You lose all the ions, the protons into the solution. Excuse me. This is a monoprotic acid, meaning one. So here, down here, I gave some very general terms of this, but these are the three acids that everybody's going to be assigned one of them or two of them, depending on what they give you. So monoprotic, this is what we use for the first titration. And I even broke it apart into the ions so you can see what it looks like. Because if you're wondering how this is balanced, remember, if these numbers subscripts are down, this is a crisscross. Monoproduct, one proton. Diproduct, two. If it has two protons, you have to have 2 moles to neutralize the 2 protons out. If you have 3 protons in the unknown acid, you need 3 moles of sodium hydroxide to neutralize it out and just make sure it's balanced. Not really anything different. You just have to account for the moles of sodium hydroxide, but the rest of the steps are okay. So you just got to add a little stoichiometry in here, and it's fine. You're not asked to know this, but I wanted to explain how a pH indicator works. You will definitely get to know more of this in 24B. You will, I don't know, with us being online, but if you weren't, you definitely would get to know these. These are titration curves. What it does is it starts out with the acid, and it's usually around pH 0. And sodium hydroxide is added. So as the sodium hydroxide is added, as you can see here, the volumes, it doesn't change, and then all of a sudden it's going to jump. And this is why students don't like titration, some of them. Sometimes this huge jump is 1 drop. It depends on how patient you are. And I have found that a lot of my students are not very patient. So they go past this. And unlike other labs, this is colored. So it instantly shows, based on how deep the color is, how far off you are. So that's why they can really see that they were not as patient as they should have been. So it's clear, the pH indicator, and then when it hits a certain indicator, so let's say around pH 8, so if it gets around there, it's going to change color instantly. It's going to go from clear to change of color and like that. So this is how it works. The pH goes up, and as the addition of the sodium hydroxide is added, the pH goes up until eventually the color change happens and the titration is over. That is for a monoprotic acid. These are diprotic acids. This one gives a little bit more information, so I'm going to refer back to this one instead. When it first starts out, it is triprotic, so it's the H3A. But as you start adding base, it interacts with the proton that is removed from it, and you can see it's now H2 with an ion, with a charge. As you keep adding base, this is now going to be removed. A second proton is removed, and it's now got a 2- charge on it. As you keep adding more base, keeps going on, it is now no protons are there, they're gone, and it is just an ion or an anion with a 3- charge on it. So that's where, if you go back and refer to what I broke down here, that's what you're seeing. So over here, little less curves, but all of this accounts for the loss of protons as it goes on. Do you need to worry about this now? No. You're just going to go from determining what you start with to what you end with. You will do way more with this, trust me, in Chem 24B. But I wanted you to see what happens. Here's a picture I found just a general picture of the steps that you would do for titration. Starts out with one color, changes color. You can see the base is still blue, but this is a red. Don't worry about these volumes. You're not going to use these volumes. Take everything off lab flow. Standards. The known amount of the substance for analysis is generally measured and available in two ways. As a primary standard, an accurate mass and moles of a solid substance is measured on a balance dissolved in water and then reacted with the substance being analyzed. As a standard solution, a measured number of moles of substance is present in a measured volume of solution, generally expressed as molar concentration or molarity of the substance. A measured volume of the standard solution then reacts with the substance being analyzed, a very well-known concentration of solute. What does this mean? Well, I'm going to explain this a little bit more as we get into the actual lab, and then this will make sense. So part A, standardization, there's that word again, of sodium hydroxide. Solid sodium hydroxide is hygroscopic. It means it absorbs water very quickly. So I've used it. It's kind of messy if you're not careful, and you don't want this stuff touching your skin. It looks like these little pellets, but what happens, and what you didn't see after this picture was taken, that this liquefied, completely liquefied. There's no remnants of a pellet. It comes into contact with water and just liquefies within a matter of seconds. Maybe it depends on how much you also have out. So you cannot accurately measure this. It's a solution. You can't do it. You can't take some away, put some in there. It just doesn't work. So we need to use sodium hydroxide, but we need to find a way to accurately determine the concentration. This is where a primary standard comes in. We are going to titrate it with something else that's going to allow us through calculations determine what the actual concentration is of it. So in this case, this primary standard, that's where this word is for number one, comes in. We're going to use dry potassium hydrogen thiolate. It's the last time you'll ever hear me say that. We simply call it KHP. And here it is. And I have given you the actual balanced equation in here. So we are going to react our unknown concentration of sodium hydroxide, but we will know the volume. And we're going to react it with the KHP to determine the concentration. Why are we doing this? Because the KHP is ideal for us to do it. It has a high purity, and it's only slightly hygroscopic. So it means it reacts well with minimum impurities, which is not going to affect our concentration. So in my lab, we actually do this. My students do 3 titrations of this and then determine the molarity for each titration of the base and then take the average, which is what you're actually going to do on lab flow with this. So primary is the one that we're using to determine the concentration, primary standard of sodium hydroxide. Once we accurately determine the concentration, molarity of sodium hydroxide, our sodium hydroxide has now been standardized. That's the second one. And we can use it to determine the concentration of our unknown acid. So we start with the primary, determine our concentration of sodium hydroxide. Once we accurately determine our concentration of sodium hydroxide, it is now standardized. So when you hear the word standardized, that's what it means. It has gone through a process in order to determine what that concentration was. And then we can take it to go on to part B and determine the molarity of our unknown acid. So this is the information that was given to me. Take all your information from LabFlow, read how to do the titration in the PDF, but it's got some numbers in there, minus the KHP mass, which is okay. Don't take any of the information in there. Just take it all from LabFlow. Okay, but the KHP molar mass is not wrong. All right, so this is the information that was given to me before I started titration. I'm not going to also cover prep. Prep is in your directions. You should be able to fairly understand what that is, and if not, you can post a question and harmonize, and let me know, and I will let people know, or contact me. So here are the steps to determine how to standardize sodium hydroxide. First things first, you need a balanced equation. Become fairly comfortable doing balanced equations. They are the one thing that will never go away in chemistry. You will do a lot of them in Chem 24B too, depending on what you're doing. So you should become fairly comfortable. If you don't like this equation that I broke up, I kind of made it, I used the KHP. I have the real one here, and so you can refer back to this one if you need to see it. And on 6.2 in your PDF, it shows you the balanced equation, but doesn't ions, which I don't like. So that's why I'm giving it in two different ways. Whichever way makes you comfortable and helps you understand what's going on, use whichever one. All right, so I balanced this out, and now I'm going to determine the volume that was dispersed from the Brett. So I have that. That was given to me in my initial and my final, and I converted to liters. Now I'm going to determine the moles of KHP. So I was given this mass sample, and I'm going through stoichiometry to determine the moles. Because this is a 1-to-1 ratio, once I determine the moles of KHP, I now know my moles of sodium hydroxide. Molarity is moles over liters. I plug in my molarity, my moles. I know what my liters is. I plug that in, and I now have my molarity for my sodium hydroxide. You're going to do this 3 times, then you're going to get the average. This, by the way, molarity, you're going to use this for parts B and C. This is the only part that you're using. Everything else is separate from each section. But this part, whatever you calculate as your average, you're going to use that. Okay, so this should not be too bad. You actually did something like this very similar in the Lab 9. Now it's going to change a little bit. You also did this part in Lab 9. However, now we have 3 different types of acid. So if you get a monoprotic acid, it's definitely the same as Lab 9. If you get a diprotic or a triprotic, it's not. So I was given a triprotic acid. I was given an unknown number, but you guys don't need to know that. My volume, this is what's in the flask on the bottom of the Brett. And then my readings and my average molarity of my base. First things first, balanced equation for my unknown acid. I make sure I have my 3 moles accounting for the neutralization. I determine the NOH volume dispensed. That shouldn't be difficult. If you need to refer back here, you can see how to do it. I just jumped ahead and gave you the number, and then I convert it to liters. Determine the moles. So here I have my liters. I have my molarity that's taken from part A, and I get my moles of sodium hydroxide. I determine my moles. This is the step that's different. Determine my moles from the balanced equation. So I have my moles of sodium hydroxide, but I have to account for the 3 moles in the balanced equation, which I do. And it produces the moles of my unknown triprotic acid. Make sure you do the step. First time I went through lab flow, I think I've mentioned before, I go through lab flow like 15 times because it's not user-friendly, and I'm trying to understand everything that can be asked of you guys. Hopefully I get everything, but I don't think I always do. I didn't do this part, and I got it wrong. So make sure that you pay attention to this part. I couldn't figure it out for a minute. Then I remembered, nope, I got to use stoichiometry. So I was given a triprotic acid. I cannot use it, do the calculations like it's a 1-to-1. That's not going to work. Now I can determine my molarity, which I have my volume that was given to me here for my volume acid. And then I have my molarity, my moles of my triprotic acid, plug it in, and it's giving me my molarity of my triprotic acid. By the way, all my numbers don't always match the sig figs, and that's because lab flow is kind of weird about stuff. So these numbers that you see that I present to you, that's where I've got the answers right. So I realize that they don't always follow sig figs, and most of the time they do, but for some reason things are just a little weird on lab flow. So if you're wondering why sometimes I don't follow the rules, it's because I got the numbers right with these sig figs that I'm using. All right, third part. I was given an acid, a triprotic acid. I don't know, and it doesn't even matter if it's the same from part B because we're doing entirely different calculations. But make sure you pay attention to the acid that you're given in part C and part B. I don't know if they separate them out or not. I'm also given a molar mass. Make sure you pay attention to what's on here and not what's in the PDF, which only gives you for, I think, as an example, as a monoprotic acid. Don't do that. Take everything off lab flow. Gives me my mass sample, my Brett readings, and my molarity from part A. So we can begin. Very simple up until we get to part 5, number 5. Balanced equation, I have it here. I have my volume that's been dispensed. I change it to liters. I'm going to determine my moles of sodium hydroxide. Figure that out here from my molarity from part A, my average. And then I'm now going to determine my moles, which same thing, 3 moles here since I had a triprotic acid again. I determine my moles of acid. And now part 5, it's different because we don't care about the molarity anymore. We want to know percentage by mass. So I need to get the mass of this in order to get the percentage. So they gave me my molar mass, and I'm just going to solve using that. So I have my moles, set it up. I now have my mass, my sample in grams of my unknown acid, and now I'll do percentage. Remember, percentage is parts over a whole. So I have my part over the whole that was given to me in my original information, and I times it by 100. So my determine the percentage by mass of the acid is 0.442%. And that's it. The lab isn't overly difficult. I'm hoping that because you did the titration before and you've been doing calculations, a lot of the stuff should be becoming a little easier, hopefully. If not, again, you can always contact me. You can post a question. I prefer you post the question first. I realize not everybody checks their stuff, and I'm not sure if the notifications are just not going out. But you can always contact me within an hour, and I will always post for you. And I appreciate anybody that gets on there and helps. It really do. I think honestly, the more you guys can help each other is a lot better than me just providing an answer. So, excuse me. This is the end of the lab. It's not too difficult. Just pay attention to what LabFlow gives you and make sure you use that information. Okay, and with that, have a good night.